9th Standard ICSE, Chemistry Chapter 4, Atomic Structure and Chemical Bonding, textbook, Anita Prasad. The introduction is not in syllabus, but good to know information. Knowledge about atoms started with the early scientists and philosophers like Democritus and Aristotle. John Dalton gave the atomic theory, but many of his postulates were proved wrong later. He said that atoms are indivisible, but now we know that atoms can be smashed in particle accelerators and they are made up of smaller particles like electrons, protons, and neutrons. And he said that all the atoms of an element are alike, but it need not be so because isotopes of the same element have atoms which are a little different from each other. J.J. Thomson gave the plum pudding model where the electrons are embedded in a positive pudding. Then Rutherford did an experiment and he discovered that actually most of the atom is hollow. And then he came up with the concept that all the positive charge is actually concentrated in the nucleus and the electrons must be orbiting around it. Then Niels Bohr explained how the electrons actually orbit around without falling into the nucleus, because the nucleus is positively charged and electrons are negatively charged. So there is an electrostatic force of attraction between them. But then he gave birth to the quantum theory, and many scientists developed quantum mechanics, which is one of the most accurate theories and one of the most complicated theories of modern science. James Chadwick later discovered neutrons, which is a neutral particle found in the nucleus. It does not participate in any chemical reaction, but it does have a significance as far as the physical properties are concerned, like density, melting point, etc. That is why isotopes which have same number of protons but different number of neutrons have the same chemical properties but different physical properties. And then the modern theories tells us that atoms are nothing like the solar system model. In fact, we have something called orbitals, which is a very complex concept which will be studied in college level. So right now we'll study the structure of an atom with the solar system model, which is not accurate, but for school level introductory chemistry, it's a good enough theory. The nucleus has protons and neutrons, and all the mass is concentrated in the nucleus. So the atomic mass is approximately the sum of the total number of protons and neutrons, or the nucleons. Electrons are not counted while calculating atomic mass because they hardly have any mass. The mass of one electron is 1 upon 1840 of a proton's mass. However, the charge of an electron is equal to the charge of a proton, and the difference is that the proton is positively charged and the electron is negatively charged. Neutrons don't have any charge. The mass of a proton and a neutron is almost same, equal to around 1 AMU, atomic mass unit. So when you talk about atomic number, it is defined as the number of protons in the nucleus, which is equal to the number of electrons if the atom is neutral. But for an ion, like a cation or an anion, the number of electrons will not be equal to the number of protons. And that's why an ion is charged, whereas an atom is neutral, because the number of positive charges and negative charges are equal. Here are some experiments. If interested, then you can read about them, how these scientists brilliantly deduced the structure of an atom, even though nobody has ever seen an atom till now. Not even with the most powerful microscopes can we ever see it. It's too small. As I told you that the solar system model given by Rutherford had some problems, due to which Niels Bohr had to refine the theory. The problem with the model was that the electron should spiral into the nucleus and fall into it because of the opposite charges attracting each other. But then Bohr's theory was developed, which is the modern and currently accepted theory. Roman number 1 cancelled. He said that electrons can only orbit in fixed orbits or shells. So spiraling is ruled out. And he called them as energy levels because electrons would have particular energy to be in one of these orbitals. And if the electrons want to jump from one orbital to another, they need to lose or gain a particular quanta of energy. And hence the theory is called a quantum theory. He named them as K, L, M, N, O, P, and so on. Now it's to be noted that each shell actually has sub-shells also, like orbitals called S, P, D, F. But that is not in our syllabus. Roman number 5 is cancelled. Discovery of neutron also cancelled. But if your school teacher wants you to learn the names of the scientists who discovered various things, then do learn them. Personally, I feel that we should just learn science and not history of science. Table, learn it. Mass can be ignored. No need to learn that. Learn the symbols, how to write them, including the subscripts, which shows the charge. And by 1 unit charge, I mean 1.6 into 10 raised to minus 19 coulomb. That's the unit of charge. Mass of proton and neutron is approximately 1 AMU, and that of electron is negligible. So the subscript tells us the charge, which is similar to the atomic number, and the superscript tells us the mass, which is almost 0 for an electron. Atomic number, mark the definition. Mark this as a give reason. This is cancelled, but it's an interesting information. It says that perhaps the protons themselves are further made up of quarks, which are very tiny particles, and quarks cannot be further broken down. But there is one theory which suggests that perhaps the quarks are made up of strings vibrating with a particular frequency. That's a string theory, but there's no evidence of that yet. Gluons are the particles or energy which holds the quarks together inside a proton or inside a neutron or inside the dozens of particles which exist. Yes, there are many particles which exist apart from electrons, protons, and neutrons. Note is a give reason. Mass number, mark the definition. An atom's weight, atomic weight, is actually in decimal, and that is defined as the number of times the weight of an atom is heavier than 1/12 the weight of a carbon-12 atom. But we take a shortcut while calculating mass number. We just count the number of protons plus neutrons, which gives us a good approximation of the atomic weight, the relative atomic weight or relative atomic mass. So the mass number of magnesium is 12, but the relative atomic mass of magnesium need not be exactly 12. It's something else. It's in decimals. Next, electronic configuration. But before that, if I give you a symbol like this, let's find out some facts about this atom. Atomic number is 12, mass number is 24. Atomic number is 12 means it has 12 protons in the nucleus. So it must have 12 electrons as well, because an atom is neutral and there is no charge mentioned. And how are these electrons distributed, or what is the electronic configuration? Well, there are some rules which we'll study shortly, but you already know that the electronic configuration of magnesium is 2, 8, 2. So it has 3 shells. 2 shells, 2 electrons in the last shell. So its valency is 2. It's a metal. It will lose electrons to become stable. Mass number is 24, meaning the number of protons plus neutrons is 24. So if number of protons is 12, then number of neutrons is mass number minus atomic number, which is 24 minus 12, which comes out to be 12. It's a coincidence that the number of protons and neutrons are equal in this case. It need not be the case. For example, in sodium, it has 11 protons and 12 neutrons. So its mass number is 23 and atomic number is 11. Yeah, there are other isotopes of sodium as well, like sodium 24. How many neutrons will that have? Electronic configuration, mark the definition. Now there are some rules given by Bohr and Bury. First rule says that the maximum number of electrons ever possible in a shell is given by the formula 2n squared. So if you talk about the fourth shell, for example, then 2 into 4 squared is 2 into 16, that is 32 maximum electrons possible in this fourth shell. However, while writing the electronic configuration, if the last shell has more than 8 electrons, then that will not be allowed. It has to be shifted to the next shell, no matter what the capacity is. For example, let's talk about calcium. Calcium atomic number is 20. So you may think the electronic configuration can be 2, 8, 10, because the third shell can have up to 18 electrons. So why not just 10? But then that is against the second rule, which says that the last shell, no matter what the capacity, cannot have more than 8 electrons. So let's write it as 2, 8, 8, 2. And there is one more law which says that the second last shell cannot have more than 18 electrons. However, that is not so important because we are going to learn the first 20 elements deeply. And the first 20 elements don't have any 18 electrons in any shell. To draw an atom, cancel all this. Nitrogen, well, 7, so 2, 5. The first shell should have 2 electrons and the second shell should have 5 electrons. That's called the valence shell. So it has 5 valence electrons. In order to complete its octet, it would share or gain 3 electrons. So its valency is 3, hence it's a non-metal. Learn the first 20 elements by heart. That is one of the foundations of school level chemistry. You can remember it with some trick like, for example, hum hai ladkiyan beautiful, brave, caring, not over smart, foolish, naughty. Na mango Aladdin se, paisa sona chandi, or Kit Kat Cadbury, or whatever works for you. Also remember their electronic configuration. Well, if you know the atomic number, then you can easily deduce it. And from that, you can deduce the valence electrons, and from that, you can get the valency. Notice that sodium has valency 1, magnesium 2, aluminum 3, because all of them would love to lose these valence electrons to achieve an octet state. They want the last shell to be complete, like the nearest noble gas, which is neon for these elements. Silicon, it is 4, but it will not give away 4 electrons. It would rather share 4 electrons. Phosphorus, the valence electrons is 5, but it will not give away 5 electrons. The nearest noble gas for these is argon. So they would gain electrons, hence they are nonmetals. Silicon is a metalloid. It's written non-metallic, but actually it's a metalloid. It has some metallic properties as well. So phosphorus, even though the valence electrons are 5, valency is 3. Don't say minus 3. That is only if it forms an ionic bond. But in a covalent bond, there is no positive or negative charge. More about that later. Sulfur would like to gain 2 electrons or share 2 electrons to complete its octet and become like argon 2,8,8. So its valency is 2. Chlorine's valency is 1. So notice how the valency goes 1, 2, 3, 4, 3, 2, 1, 0. Yes, noble gases have 0 valency because they are already stable. Their last shell is complete. They will not share or transfer electrons unnecessarily. However, at very extreme pressure and temperature, we can force them to undergo chemical reaction, but normally they don't react. Hence, they're called inert. Some scientists call them nonmetals, but some call them just noble gases, a separate category. Now mark the definition of valence electrons and of valency. Then mark the definition of electronegative elements and electropositive elements. So metals are usually electropositive because they lose electrons, and when they lose electrons, then there is a deficiency of electrons. So the number of protons is now comparatively more. For example, after aluminum loses 3 electrons, it still has 13 protons. Number of protons don't change in a chemical reaction. They can change only in a nuclear reaction. So 13 protons, but now only 10 electrons left. So it has a deficiency of electrons, hence it becomes positively charged. Plus 3 will be the charge of this cation. And electronegative elements are typically the nonmetals because they gain electrons and become anions. Look at these electronic configuration. Although you don't have to remember them because you only have to remember the electronic configuration of the first 20 elements. But it's interesting to note that these elements, they follow the rules like last shell does not have more than 8 electrons, second last shell does not have more than 18 electrons, despite the capacity being much more than that. Now the octet rule, mark it. I've just explained that. But not all elements follow the octet rule. The first few elements, that is hydrogen, helium, lithium, beryllium, boron, they obey the duplet rule. That is, since their first shell itself will become their last shell, and the first shell cannot have more than 2 electrons. They do not need to have 8 electrons in their first shell. They can be stable by just having 2 electrons in the first, which is the last shell. So hydrogen just needs 1 electron, helium is already stable. Lithium wants to lose 1 electron, beryllium would like to lose 2 electrons, boron would like to lose 3 electrons, or maybe even share some electrons. You see, boron is a metalloid. It's not a good conductor of electricity like typical metals. It's something to do with its small size. The electrons are very close to the nucleus, so it's difficult for it to readily lose the electrons. Carbon is a non-metal, somewhat like a metalloid, but mostly a non-metal. Now, isotopes. Mark the definition. Look at protium, deuterium, and tritium. Protium is the only atom in the periodic table which has no neutrons at all. The atomic number and mass number is same. But if it does have 1 neutron, then we call it deuterium, and mass number becomes 2, whereas atomic number remains the same. So the chemical properties of all 3 are the same. Valency is same, just the physical properties are different. For example, deuterium and tritium are a little heavier, and the water molecule formed from them is called heavy water, useful for nuclear reactions. So mark this as a give reason and this as a give reason as well. You see, atomic number decides the chemical properties, not the mass number, because atomic number decides the number of electrons, and that decides the electronic configuration, and that decides the valency, and valency decides the chemical properties. Carbon has isotopes as well, but these heavy isotopes are quite rare because they're unstable. You see, when the number of neutrons are greater than the number of protons, they will slowly decay to become stable, where number of protons and neutrons are equal or almost equal if it's an odd number. For example, in sodium there are 11 protons, so it can have 12 neutrons to be stable. It doesn't have to be equal. In fact, carbon-14 decay is useful for finding the age of fossils. We can know if it's 1 million years old or 20 million years old through carbon dating. No, that's not going on a date with carbon. Now this is also a GR. All isotopes are kept together in the periodic table because periodic table is arranged in order of the increasing atomic number, not mass number. More about it in chapter 5. Chlorine has two atomic numbers, 35 and 37. So the average is taken as 35.5, which is quite surprising because the average of 35 and 37 is 36. But still we say that the atomic weight of chlorine is on average 35.5 because 75% of all the chlorine found in nature is of 35 variety. So there is a weighted average. The average tends to shift towards the 35 end. So mark this as a GR. Although the percentages are not important. Chemical bond. Mark this as read. Cancel this. Now there are two types of chemical bonds. Mark the definition of chemical bond. We are going to study electrovalent bond and covalent bond. There is also something called coordinate bond, but that you will study in class 10th. It's an interesting bond. Remember, electrovalent bond is formed only between metals and non-metals because there is a transfer of electrons required. And covalent bonds are formed only between two non-metals where sharing of electrons is required. So here cation and ion is formed, here no ions are formed. Is a bond form possible between metal and metal? Yeah, there are some metallic bonds, but that is not in our syllabus. Now mark the definition of electrovalency and electrovalent bond and even electrovalent compound. Let's take this example. Now whatever diagrams are double ticked, you have to practice them. Pro circle is compulsory. You can show the electrons with a dot. All shells have to be shown. Before and after, arrow, square brackets, plus and minus signs. Be careful about all these things. Sodium has electronic configuration 2, 8, 1. It would love to lose one electron to become stable like the nearest noble gas, which is neon. Chlorine has electronic configuration 2, 8, 7. It would love to gain, don't use the word love, to gain in school exams. It tends to gain one electron to become stable like the nearest noble gas, which is argon, 2, 8, 8. So a transfer happens, it's a match made in heaven. But sodium becomes positive when chloride becomes negative. You see, positive people give and negative people take. Their octets are complete, they are stable. But at what cost? Now opposite charges attract each other, so they are stuck with each other, and a new compound is formed, sodium chloride, and this is the molecule of that. This was the orbital diagram. We can show the same thing with electron dot structure as shown here, which is easier because now we don't have to show the circles, no stencils required. We can do it freehand with a pen. However, such diagrams are there in 10th standard. In 9th standard you have this. But if your school teacher teaches these diagrams as well, then better learn it. Now same logic for magnesium chloride. It has 2 electrons to lose to become stable, so it searches for somebody willing to take 2 electrons, but it can't find anybody. The only option available is chlorine, but chlorine can take only 1 electron, so it has to use 2 chlorine atoms to satisfy its wish. And so magnesium becomes 2 positive, chloride becomes 1 negative, chloride becomes 1 negative, and MgCl2 molecule is formed, ionic bonds between them. Look at the cross and dot structures also. Don't forget the square brackets and the signs. Yeah, instead of drawing chloride twice, you may write 2 into chloride. Calcium oxide, same logic here. Calcium loses 2 electrons and oxygen gains 2 electrons, and an ionic bond is formed between them. They are stable, octets are complete. Now, metals lose electrons. So this part of the equation is called oxidation reaction, loss of electrons. And non-metals gain electrons. That part of the equation is called reduction. So this was a redox reaction where reduction and oxidation take place simultaneously. Metals undergo oxidation, but they reduce others, so they are called reducing agents. And non-metals undergo reduction themselves, but they oxidize others, so they are called oxidizing agents. So remember, Mr. No, metals are reducing agents, non-metals are oxidizing agents, but they themselves don't go on oxidation, they oxidize others, they themselves undergo reductions. Yeah, sounds hypocritical. But more about reduction and oxidation in chapter 6, hydrogen. Ionic compounds, properties. Since there are cations and anions, they have a strong electrostatic force of attraction between them. That is why they are all crystalline, hard, brittle solids. And they have high melting and boiling points because the bonds are strong between the ions. So mark this as a GR and a GR. And they are generally soluble in water. You see, water is also a polar compound, meaning it has a charge separation. Like dissolves like. So in water, the oxygen is slightly negative and hydrogen is slightly positive. So there are opposite poles developed. Hence it's called polar. Even though it's covalent, it does have some properties of ionic compounds. So that is why ionic compounds can dissolve in water. Mark it as a GR. Whereas non-polar compounds, for example, methane, CH4, their covalent bonds, they don't have any charge separation. It's non-polar. They will dissolve not in water, but in other organic solvents, which are also non-polar. more about covalent bonds later. Next point, also a GR. These ionic compounds are poor conductors of electricity in solid state because in solid state they don't have any free ions. But once you dissolve them in water, well, water is a high dielectric constant. I say it's a great divorce lawyer, so it will break the bond between them, create the cations and anions, and more the free ions, better a conductor it is. And not only when dissolved in water, but even if you melt it at a high temperature, the bonds will break, ions will be formed, and it will become a good conductor of electricity in the molten state as well. Mark it as a GR. Mark the definition of oxidation and reduction here. Mark this as read. This is all the intense standard. They're saying that cations are smaller than atoms and anions are bigger than atoms. Now, exception to octet rule. Mark it as read. This is college level stuff. It says that octet rule and all is good for school level, but in higher standards, you will realize that atoms can be stable even when octet is not completed. Examples, barium chloride and phosphorus pentachloride. But we don't have to get into this right now. It's not in the syllabus of school level at all. Now, covalent bond, which happens only between non-metals because neither is willing to give, both are dying to take. So only sharing is the available option. Mark the definition of covalency and covalent bond. And remember, sharing is a covalent bond. For example, here, hydrogen would love to get one electron to complete its duplet like the nearest noble gas, which is helium. But it can't find any metal. And yeah, it behaves like a non-metal right now. So the only option left is bond with the same type. If you can't find somebody of the opposite type, some atoms do bond with the same type. Hey, it's a democracy, whatever works. And this shared pair of electron is called a covalent bond. Notice that there is no cation or anion here. Same thing can be drawn with the electron dot structure, freehand. Chlorine, even they have a shared pair of electrons, so we say they have a single covalent bond. Notice that by sharing, they think that they have an octet complete in the last shell. So 1, 2, 3, 4, 5, 6, 7, 8. Even this atom thinks 1, 2, 3, 4, 5, 6, 7, 8. So octet is complete, they are stable, but that means that to remain stable, they will be bonded together. Very few people like noble gases can stay single and be stable. Otherwise, mostly all the atoms need to bond with somebody to become stable. So what kind are you? Oxygen. Electronic configuration is 2, 6. The first shell is not shown, which is okay if your school teacher is okay with that. Otherwise, show the inner shells as well. So all these double ticks have to be practiced, and as of now you can draw the way it is in the textbook. But make sure you do use the stencils or the pro circle. Freehand won't be allowed. These diagrams you need not practice. That is on hold. Check if your teacher teaches this, then only practice them. But they are their intense standards. You might as well study them. Notice that to be stable like the nearest noble gas, which is neon, it would like to gain 2 electrons. It's searching for calcium or magnesium or sodium, but there is no metal available. So it will form a bond with another oxygen atom. They will share a pair of electrons, meaning two covalent bonds have been formed between the same 2 atoms. So we call it a double covalent bond. And with this, their respective octets are complete, they are stable. And O2 molecule, oxygen molecule is formed. So even chlorine is diatomic even though valency is 1, and here even oxygen is diatomic even though the valency is 2, and even nitrogen is diatomic even though the valency is 3. So there is no connection between valency and atomicity. It's just that here 3 pairs of electrons are shared for each atom to become stable. So we call it a triple covalent bond. What about HCl? Well, again, it's a single covalent bond. This completes the duplet, this completes the octet, single covalent bond. But here chlorine is slightly more electronegative, or I would say greedier than hydrogen. So the shared pair of electrons are closer to chlorine and far away from hydrogen, almost as if hydrogen has transferred the electron. But it is not as generous as sodium, so it won't become a cation, and chlorine will not become an anion. It is a covalent bond, but I would say that it has a slight negative charge, delta minus, and a slight positive charge. So it's a covalent bond, but it does have some ionic properties, and such a bond is called a polar covalent bond because it has opposite poles, just like water was a polar compound. So will HCl dissolve in water? Yes, like dissolves like. So since it has poles charge separation and water does as well, so it will dissolve. In fact, all acids dissolve in water. By dissolving in water, they become acids. Electron dot structure is like this. We can also use crosses, to distinguish between the electron of one atom and the other. We can use a cross for one atom and dots for the other atom, because in exam we can't use different colors as they have. So water and ammonia are again examples of polar covalent bonds, but that is not in our syllabus. It is intense standard. However, if the school teacher teaches it, then remember this concept. So here we have two single covalent bonds. We can't call it a double covalent bond. And here also we have three single covalent bonds. We can't call it a triple covalent bond, because triple covalent bond, which is in nitrogen, happens between the same two atoms. But here, how do we say it? Look at the language here. The nitrogen shares a pair of electrons with each of the three hydrogen atoms to form three single covalent bonds. And this pair of electrons which does not participate in bond formation is called a lone pair, which has some significance in 10th standard. Now, methane. Well, here 4 pairs of electrons are shared for the carbon to complete its octet and for each of the hydrogen atoms to complete their duplets. So we have 4 single covalent bonds formed, and these are non-polar. This one is a non-polar because the electronegativity difference, the greediness of carbon and hydrogen is same, so the difference is negligible. So they will not dissolve in water. They will dissolve in other non-polar or organic solvents like carbon tetrachloride or petrol or benzene or toluene. Carbon tetrachloride is a liquid. So I see that carbon has formed a single covalent bond with each of the 4 chlorine atoms. So practice this diagram. Now copy this extra information. In polar bonds, the shared electrons are unequally distributed between 2 atoms. In non-polar bonds, the shared electrons are equally distributed between 2 atoms. Now, properties of covalent compounds compared to ionic compounds. Ionic compounds are made up of ions, whereas covalent compounds are made up of molecules. There are no ions. Now, the covalent bond is strong, but between 2 molecules, the intermolecular force, also called van der Waals forces, are quite weak. So, unlike ionic compounds, covalent compounds exist like gases and liquids or soft solids, whereas all ionic compounds are hard solids because of the strong electrostatic force of attraction between the ions. There we had high melting and boiling points, but here we have low melting and low boiling points because of the weak intermolecular forces of attraction. They are insoluble in water usually, of course there are exceptions in chemistry always, and they are mostly soluble in organic solvents. But yeah, polar covalent compounds will be soluble in water and organic solvents also perhaps. They are bad conductors of electricity because they don't have ions. Even in liquid state, and when I say liquid, I don't mean dissolved in water, they don't have ions, so again they will not conduct electricity. They have a slow speed of chemical reaction. Mark all these as GRs. Slow speed because the covalent bond, not the intermolecular force of attraction, the covalent bond is quite strong. So a lot of energy will be required to break it and make new bonds. And study all these study material. Solve the exercises, page 55 entirely for homework. Also solve page 136, 137, 138, 139, 140, 141, 142, 143, 144, 145. Yeah, all this is for homework. Hi students, this is AJ sir. If you found this video useful, press the like button. Also, if you'd like to enroll for my test series or online lectures, email me or message me on Instagram. Check my description for more information.